E agora eu vou chamar o nosso keynote internacional, que é o Joe Graham, também conhecido para a gente que é da velha guarda como Kingpin. Ele é engenheiro de computação, hardware hacker, designer de produto, professor, conselheiro, corredor, pai, doutor honorário, apresentador de TV, membro do lendário Loft Heavy Industries, talvez um dos grupos hacker mais influentes de todos os tempos, proprietário do Grand Idea Studio, e ele tem criado, explorado e manipulado sistemas eletrônicos desde os anos 80. O título da palestra dele é Setec Astronomy, An Overview of Hardware-Based Covert Channels. Covert Channels são métodos de transferência clandestina de dados usados para se comunicar ou exfiltrar informações de um sistema de computador comprometido. Eles podem existir em qualquer camada do sistema, incluindo hardware, software, aplicativos, sistemas operacionais ou na camada de rede. Normalmente os Covert Channels são empregados em ativos críticos, protegidos, ou com air gap que o invasor pode não conseguir acessar por meios convencionais. Nessa apresentação, o Joe Graham fornece uma visão geral dos Covert Channels baseados em hardware e demonstra algumas técnicas que podem ser facilmente implementadas com eletrônicos prontos para uso. Como vocês já sabem, as palestras, por restrições técnicas internacionais, elas são em inglês. Se teu inglês não está muito bom, sabe o que você faz? Se esforça. Continua olhando a palestra mesmo assim, uma hora tu começa a entender. Mas depois, quando a gente soltar a palestra, na semana que vem, nas semanas seguintes, a gente coloca a legenda e tu aproveita para revisar os teus estudos de inglês. E uma coisa eu digo para vocês, precisa aprender inglês, senão a carreira de TI não decola. Joe, thanks a lot for being here with us. I can see you have precisely a quarantine haircut like everyone else.
I'm letting it go. Yeah, it's been fun to to experiment with my hairstyles.
Yeah, no problem. And it's it's a great opportunity for us to have you here. And I'm amazed by is this your workbench? Are you really live stream?
So this is my office right here. So my kind of computer and oscilloscope and one workbench is in front of me, and then behind me is where I build the hardware. And then behind that, I don't know if you can see it, but that's where I have the 3D printer, the circuit board prototyping machine, and printers and all of that stuff.
Oh, that's really cool. And this presentation would be interesting if the only thing you've shown would be your workspace, but I know you have way more to share. Pessoal, uma salva de palmas do Joe Graham no chat do Roadsec.
Cool. Well, thank you, Anderson. Thank you, Roadsec. Thank you, everybody, for having me. Yeah, this is exciting. I like being on stage, and I like walking around and using my hands and everything. So being stuck in a chair is a little bit interesting. I had such a great time at Roadsec in 2018, Sao Paulo. It was just one of my favorite trips. Such a great experience, and I have a real kind of fondness now for the South American hacking community, especially in Brazil, everybody I met there. So coming back virtually for this is, it's an honor, and it's a lot of fun. This presentation is a little bit different than some of the topics discussed earlier. We're going to be talking about hardware because I am a hardware hacker, and that's what I grew up doing. Building electronics, experimenting with things, tweaking things, hacking things. I just like physical hardware and being able to create stuff and then modify other stuff as well. So if you do want to learn more sort of about the backstory of how I got into electronics and hardware and how I became a hacker at the same time, you can watch the keynote from 2018. So covert channels are basically hidden methods or covert methods of communicating with a piece of hardware. A lot of times it ends up being a one-way transfer. So you might have a compromised system that you need to get data off of in a way that isn't going to be detected by your traditional intrusion detection, stuff like that, antivirus, stuff that's very obviously looked at. So using these non-conventional techniques to do that. Sometimes you see covert channels also for a bidirectional communication, for like a command and control say if there's malware on lots of systems. But generally, it's like this one-way transfer is where most people, I would say, are focusing kind of their efforts. This kind of topic of InfoSec or cybersecurity or whatever you want to call it, hacking, has been around for a long time. Really, like a lot of the topics that we still work on, we're kind of standing on the shoulders of giants, and this is no different. The first mention of a covert channel was in a document from 1973 in the Communications of the ACM. So, an academic kind of engineering software journal talking about using non-conventional means. Essentially, instead of using a legitimate channel, an established channel between computers, say like your normal network packet or whatever, you're modifying things to subvert and get through in different ways. And this can exist, like my abstract mentioned, in lots of different ways, lots of different layers of the system. So, of course, I like the hardware level, and that's what we're going to be talking about in the presentation. But even on top of the hardware, you could have a computer system that not only has its motherboard, it has peripherals, it might have speakers, it might have other things, or it could be a embedded system. So not necessarily a computer like a laptop, desktop server, but a circuit board that has a microcontroller on it, where every single type of embedded system is essentially a microcontroller, a general purpose computer running specialized code. So if you're able to compromise that system, change the code, inject whatever you want, now you can use that as some sort of exfiltration method. And it goes up the stack from there. We see a lot of discussion around covert channels and operating systems, or in the network stack. So changing timings of things, basically these minute changes or minute differences that can be detected by an adversary can be recreated back into the data. There are a few challenges with covert channels, both from an offensive point of view, which is what they're generally used for, and from a defensive point of view. There are, I would say, an unlimited number of ways that you can hide when you're exfiltrating data from a system. Again, because there's so many different layers of your system, and there's just so much complexity in a system that it's essentially impossible to track everything. If you're aware of what your adversary might be using as a exfiltration method, or if you've locked down certain parts of your system and say, okay, we know our network is good, we know our physical access is good, then you can focus on other things. Maybe you do some reverse engineering of code running on your system to make sure it hasn't been compromised. But it's a very, very hard thing to detect covert channels if they're done right. Another sort of downside to a covert channel is you might be thinking, well, if you've already compromised the system in the first place, why would you need to inject something else? So this is typically done on like an air-gapped system or some physically secure asset or something, maybe in an area that isn't connected to a network or isn't normally accessible. So you have to implant in some way and then return later to try to get the data back. So it's a little, it's a little more complex than just like doing some phishing and owning somebody's machine. That would really be the first step in the process of doing stuff. So I haven't really seen, I'm trying to think if I've seen any real world covert channels that were intentionally placed there and not just demos. And I'm trying to think of that, and I'm not sure I can. I've seen papers about examples of devices leaking information by accident, sort of by misdesign of the system, which I'll mention when we talk about optical covert channels. But we know they're out there. We just don't know, how are they detected? If they are they not being made public? But it's just such a cool topic. And especially with hardware, as you'll see, like there's so many different things you can do. So yeah, you have to compromise the system first, which is a big step already, to load your malware, and then you come back later. Generally with covert channels, it is just a software or malware addition to the compromised system. You don't generally need to modify the hardware itself, though that is possible as well. And I'll talk about that a little bit. But generally, if you modify code of a system, that's going to then take advantage of your existing hardware design and then use that in a way to leak the information. And that's the cool thing about it. So as far as the hardware perspective of it, there are lots of ways that previous slide showed of implanting a system, as we know of, whether it's network, phishing, sneaker net, would it tricking somebody to put something in their computer, all of these things. But the hardware espionage section is the coolest way of injecting something into a piece of hardware, whether it is physical hardware or maybe it's just a firmware change. Tons of different ways to do it. And this is really a completely separate topic that I could talk about for days. But just as an overview of how possible it is to modify a piece of hardware, we can look at this table here, and this is from a paper back in 2010 that really hasn't changed since. That's showing you can insert, you can have the code do something. How does it get activated? Once it's activated, what does it do? Where do you put it? And this is just on the circuit board, right? So then you think about all these other levels. How can you hide stuff? And it's like, limitless possibilities. So from a hardware perspective, it could be from the design phase. As the system is being designed, you could have a malicious employee come in there and modify something. Or there was some work done at DEF CON 26 presenting some attacks against engineering development tools. So you normally think, when you're compiling code, you're writing your code, doing whatever, you sort of trust the compiler and you trust your tools to do the right thing. And in this case, it's like, what if the tools are compromised to inject information or to inject malware into the system that you don't even know about, which is really pretty scary because, I trust my tools, even to the point of like, I trust my hardware. When I go and buy something off of eBay or Amazon or whatever, I don't open up the hardware to make sure it hasn't been tampered with. I just sort of trust it. And that, goes with probably most people, right? I don't know how many people open up everything that they buy. They should, right? It doesn't scale though if you're working in an environment that has thousands of machines. And if you don't even know what you're looking for when you open the thing up, it makes it tricky. But it's something that, it's like, it's a hard thing to detect. Then as far as like the fabrication stage and the distribution stage, you're trusting different factories and different companies to manufacture physical hardware products. Where do the components get purchased from? How do you know that those are legitimate and haven't been compromised in some way where you're putting a chip on the board that says it's supposed to do one thing, but it does something else? Or it does something else along with what it's supposed to do. You don't really know. Maybe the circuit board has been compromised. Maybe some additional traces have been added to the circuit board to make it easier to do your covert channel later on, which I'll mention. The distribution stage is really cool. Various governments have done this with interdiction, basically intercepting a package that's being shipped from the factory. So a known good tested unit, intercepted when it ships from the factory, but before it gets to the end customer. And the end customer would be whoever the government is trying to, spy on or control. And then the system would, the box would be carefully opened up. The system would be compromised. Everything would be closed back up, shipped to the vendor, shipped to the end user. And now that end user is compromised. And again, unless they're opening up the device, physically looking at the boards, verifying firmware, all of these things, which if you're dealing with a complex system, you don't have access to even know what a known good standard is in the first place. So, yeah, crazy. And then, when the device is in the field, somebody could do stuff. So there are all these different levels of things. The main thing to keep in mind as we talk about covert channels is there's lots of different ways to get your covert channel into the hardware. So here are the types of hardware-based covert channels that we're going to talk about. This presentation is more of like a resource guide, where there's a few things that I've developed. There's lots of work that other people have developed, and it really is just a way for you to, get introduced to the different topics. And then if you're like, oh, I'm interested in digging deeper into that, you can look at the resources that I have. I'm sure I've missed stuff, but I've put some of the, the most recent, most relevant type of work in these different hardware covert channel kind of sections. One of my favorite to start off with is optical covert channels. And this is basically leaking information through an LED, a light emitting diode that we see on every single device out there. If you think about like a network rack, all those status LEDs, all the stuff blinking all the time, blinking lights everywhere. If malware can control those physical LEDs, they can start modulating those LEDs to send data. And it's just, the reason I put this one first is it's not the earliest type of covert channel that's known, but to me, I think it's the easiest to kind of understand the concept of what's going on. And this is something like the picture down here, I just show a standard LED circuit where we're just driving the LED from a microcontroller. But if you modulate the LED fast enough, the LED is going to appear like it's just on or doing what it's normally doing. But then at the same time, you can be leaking information out of it. And that's pretty cool. Of course, to figure that out, because the human eye can't see that, you could use an optical receiver, which I'll demonstrate. I have a little open source version that you can build on your own, or maybe like a high-speed camera system to see if you can catch modulation within an LED. A problem with doing that, though, is that a lot of LEDs on systems will already modulate its on and off using pulse width modulation to dim the LED or save battery power or whatever it is. So you might then have to extract the ones and zeros that somebody is intentionally transmitting from the already modulated signal. So again, there's lots of ways if you know where to look. So yeah, lots of examples. I'm not going to go through all of these. I just wanted to have these here again so you can kind of dig deeper on your own. But there are a lot of things going on. I will show you this demonstration. This one is a video demonstration. Then I'll give you a physical one with some circuitry that I have here as well. But this is an example of compromising a system and then modifying that system to exfiltrate data. So that two-step process of injecting that covert channel and then receiving the data from it, which is a typical type of thing. This one is a demonstration that I created. This is using a TP-Link TL WR841N access point. So just a home-based router type of thing. And it's physically unmodified, but I did load DDWRT onto it. And that's an open source kind of Linux access point type of setup, which just made it a little bit easier for me to control the LEDs, individually control the LEDs on the system. The original version of the TP-Link device is also running Linux. So if somebody was doing this in the real world, they would just compromise the original box. They wouldn't have to load DDWRT onto it. I just did it because it made it easier to write some code. And because I'm not a software person, that was the best thing to do. So what I have is a program running on here. If you look at the main screen right now, it's just a screenshot of it. But this is code running on the TP-Link device that is just called Optic Spy. And that is running and then reading. It's running as root. So again, you already have root access. It's a little bit of a cheat for the demo. But it's running as root. It's reading the Etsy password file and then exfiltrating the Etsy password file out of one of the LEDs. So here's a little video of it. And what we see on the left side is the shell from the router. There is the router. I'm controlling that WAN LED, that orange LED over to the right that doesn't look like it's blinking at all. That's what's sending the Etsy password file. This is a prototype of my optical receiver. I'll talk about that again in the next few slides. But here I just hold that up to the LED. And in this particular environment, I have to get pretty close, right? Like if somebody is in your NOC holding a device up to one of your LEDs, you should get, curious about what they're doing. But on the right side, that terminal program is showing the data being received from the optical receiver. And you can see it lines up and there's a little bit of noise in there because there's ambient light all around. But now I've received that data and then I could go use that for something else. And again, covert channels really depend on what data you want to exfiltrate out of the device. Being root already, maybe I don't need that password. Maybe there's other information that I need, whatever else it is. But that just shows you can't tell, that I'm getting stuff out of there. So besides just kind of having this resource guide, I wanted to at least have a few slides talking about things you can do yourself. Of course, reading all the papers that are out there and trying to recreate that. One of the reasons that I got into covert channels was, again, because it was easy to understand. But I read a paper that is mentioned in here back in 2002. I don't actually remember what the name is right now, but it's in there. And that talked about off-the-shelf devices that were unintentionally leaking information. So modems, it was back in 2002. So modems, different types of network devices where the LEDs, the status indicator LEDs, transmit light, receive light, were directly connected to the data lines to sort of save software overhead of having to have a separate LED control stuff. And that just got me really into it. But the problem with a lot of the papers is they didn't talk about their receiver circuitry. So it was like, all right, we know that you can do this stuff, but it would really be nice if you could build your own stuff to verify it or to demonstrate it to other people what's going on. So I ended up creating a device called Optic Spy, and that's an open source tool that you can build your own. There's a few variations of it on my website. One of them is a digital version, so it just takes, it uses like a fiber optic receiver module, which does all of the amplification and decoding and everything inside the one device. But then there's an analog version as well, which you saw in the video. And then this picture on the lower right here actually is this one. And this is an analog version. So it has a photodiode on the front and a bunch of potentiometers that you can adjust the settings of things to really, try to fine tune and target a system. So I thought that would be fun to build and to demonstrate, so you can build your own. They also have, there's some assembled units as well sold through Crowd Supply. But that way people can start experimenting with it. If you do want to build your own demonstration unit, you can use an Arduino and you can use an LED. And this is something that has very few lines of code. As you can see, there's, basically setting up a software serial port and then sending a message. And you're sending a message like a printf function, but instead of sending it to an IO pin that would be connected to a USB to serial adapter or something like that, you're just sending out the data to an LED. So that's like the simplest type of covert channel that's out there. A lot of the papers that exist talk about different ways of modulating the data to hide it even more and stuff like that. But this, by doing a printf on an LED, is using the UART interface, and it's using an NRZ encoded data stream, non-return to zero data stream. So very easy to capture and recreate. Let's see. So also on the Optic Spy page on my website, there is full Arduino code if you wanted to build your own. But this is essentially, those 3 lines of code are really all you need to do that. And to demonstrate that, I have this unit. This is part of a little board I put together to demonstrate some of the unintentional leakage from the modems from that paper from 2002. But it also is a standalone little demonstration unit. And it's an Arduino Mini, which is in the center, and a little power supply on the right side, a little micro SD card, and then an LED, and then this DB25 connector on the left. So the intent of this was you would plug this into the back of a modem, and then it would force the modem LEDs to transmit the data. But it also, standalone, we can read data from the micro SD card, which is there, which is preloaded with a little special treat for you guys. And then it will modulate the data through this red LED. So let's see if this works. I need to also share my screen again because I'm going to show the terminal program, which is there. Okay, that's good enough. So what I'm going to do, I'm going to turn on this unit. And this is also available on the website, open source. You build your own. They're super easy. These Arduino Minis are really handy. So here we can see like the red LED is on. And let's see if I can hold this up. There's so much stuff on my desk. All right, so we see some noise already. So if I move this thing around, I have a ton of ambient light in here. So it's just picking up noise. But then if I hold it close, let's see, I might have to cover it up a little bit. Yeah, love that song. So I'm hoping people are laughing right now because I think it's funny. But that LED that is not blinking at all, we can't see it, is sending that data, right? Sending a little rickroll. So that's a quick demo of an optical covert channel. Let's see if I can get back to my slides here. Good, okay. So another type of covert channel is electromagnetic or RF. This is a much more complex topic to kind of understand, but it is probably the most well-known type of covert channel out there. If you'd ever heard about tempest monitoring or Van Eck freaking, which there's a paper written by Wim Van Eck back in 1985 talking about this phenomenon. This is one that I would say kind of started it all, even though before then, different countries had known, like back with spark gap transmitters for sending Morse code, that you could monitor those emissions coming off of the, coming out of the air, off of the wires to recreate the signals. So it actually, this phenomenon is basically an electrical issue that we can take advantage of. So with tempest monitoring back in 1985, the work there was basically with those old CRT monitors that had the cathode ray tube and the ray would be scanning across the screen to turn on and off the pixels. That would generate a huge amount of high voltage, and then it would generate, because of that high voltage, a lot of electromagnetic interference. And so from a remote distance away, you could pick up that detectable noise and recreate the contents of what you were seeing on one screen on a remote screen. So sort of spying based on the emissions, the unintentional kind of emissions from a system. But knowing that you can control the currents and voltages sometimes on a system, on a board, you can then control the amount of electromagnetic interference being leaked and use that to your advantage to intentionally leak information. And that concept comes down, like I talk about here. I'm not going to get into all of the electrical details. You can see the drawing down on the right is lots of different things. But basically, as current is flowing through a trace on a board, say between signals or out of a connector of some sort, and as that signal changes, it generates emissions. It generates this a magnetic field or an electric field that could be manipulated if you have control of that signal. We also hear about electromagnetic and RF in side channel attacks. So side channel power analysis attacks, which again are when systems are unintentionally leaking information. That's a different type of attack, but using the same sort of phenomenon there. So a lot of examples of electromagnetic covert channels as well. There's some crazy stuff here of like, if you can control one of the IO pins on a microcontroller, say on a board, you could modulate that at the right way to use the trace on the circuit board as an antenna to send data out of. And lots of great examples that you could go and look at and even rebuild on your own, kind of replicate. These slides, besides being shown on the video, are available on my website. If you go to grandideastudio.com and just search for covert channels, they're actually, I just posted them right before this. So another thing we can do for covert channels would be thermal. So manipulating the temperature of a system or of a component or of the environment to send ones and zeros in some way. And as you could probably imagine, like controlling temperature is much slower of a process than turning a bit on and off. But it's possible, and there is work around this. And it can either be a direct sort of change of a component to have the temperature change. So like this video here is an example from some work some guys did for DEF CON 16 of showing I think it was a resistor on this circuit board, this little FPGA development board they were using. And they were changing the amount of either voltage or current going through it, and it would dissipate as heat. So they could control that and send, ones and zeros or something if they wanted to, but it's very slow. There was also a talk that's linked in the slides of controlling an HVAC system. So you hack an HVAC system of an office space, and then you have some temperature sensor somewhere that's sensing the changes in temperature and capturing the data that way, right? So it doesn't have to be a system level thing. It can be more of an environment. Something I learned when I was putting together this presentation is the temperature isn't only directly used to turn something on or off. It can be used, and it is used a lot of times, to affect the timing of critical functions. So if you can heat up, say, the microcontroller, microprocessor, CPU of a system by increasing the amount of stuff it has to do, that could indirectly heat up the crystal oscillator that's providing the precise timing for the system. And in a lot of crystal oscillators are not temperature compensated, meaning if the temperature changes, the oscillation could change a little bit. So it might, you do it in such a way that it doesn't break the system, whatever it's doing. But if somebody knows to look for that clock skew, then they can put stuff back together. So pretty mind blowing. This is super cool. And here are some of the examples of that. And then another one is acoustic. And this is another one that's sort of easy to understand, and you'll see there's a lot of work in this area as well, where instead of using some visual mechanism, you're using some audible mechanism to leak information. And generally, it's going to be ultrasonic, which is something that is not detectable very, very well by humans, but still functions within normal speakers, normal microphones, can capture and send audio at a much higher frequency than humans can deal with. So we can take advantage of that. And maybe that's going to be exfiltrating directly from speakers, which is an example I'll show you. Maybe it's an electronic component on the board, which is kind of cool. There's a whole phenomenon called electrostriction, which basically is like the shape of part of the component changing with an electric field. So you're kind of causing a vibration of a component or causing a vibration of the circuit board. And you've probably all seen this, like on power supplies. Sometimes you hear like a whining sound that could be caused by the inductors on the board or the capacitors or the circuit board itself. So if you can control that, modulate the power, that's going to change that sound. If you're able to do that in a way that creates ultrasound, so upwards of, say, 16 kilohertz, then you get outside the range that humans can detect, and then you could take advantage of that. If we look on this chart in this lower left picture here, generally humans can hear up to about, I think it's like 20 kilohertz, maybe as high as 28 kilohertz. It depends on how many concerts you go to and how old you are. There is a wide variety, but generally it's like when you get to 20 or 30 kilohertz, humans are not going to be able to hear it. Lots of animals will, the dog whistles, a lot of marine mammals, bats use it for echolocation. So it's cool. Like a lot of animals are already using acoustic, channels to communicate information intentionally. So we just want to do the same thing. This picture on the right is from a piezo sounder module, so a piezo transducer, that's showing the amount of the sound level, the volume of the signal at the different frequencies if you feed that frequency signal into that unit. And it gets pretty loud above 16 kilohertz, but it keeps going. So that's why you could use a standard type of element on a system. If you can control that element, now you can modulate that in a way that you can't hear it. And I'll show you that in a second. So lots of examples here as well. Just super cool stuff. And besides directly communicating or directly controlling a speaker element, there are some examples of directly controlling a power supply, again, to create noise that you can use, or even controlling a mechanical motion of a hard drive head to generate sound that you can pick up. So yeah, kind of cool. So here's a demonstration that I'll give. And what I have here is, we can switch to a full screen view. This unit here is a circuit board that I use in some of my hardware hacking training classes. It's just a microchip PIC-based microcontroller with some LEDs. And generally in my classes, I have a little security mechanism and you have to analyze the board to defeat it. But in this case, I have a little covert channel that I built in here. And it's an optical covert channel. So it's on right now. And I'll hold it up to the microphone. I don't know if anybody can hear that. I'm assuming no. I'm hoping no. But it's sending information. And then I have a little bat receiver module. And this was a kit. I have a link to it on the next slide. This is a kit put together by a hackerspace in the UK that basically takes ultrasonic frequencies and down converts them to levels that we can hear. So it divides the frequency down. And this is actually used for listening to bats talking and stuff, in the evening time. But it's a great way to do like a quick and dirty demonstration and detection of covert channels. So I'm going to put my battery in. It's annoyingly loud, so be prepared. Let's see if I can move it around here. Actually, I have some Scotch tape. So I'm going to take some tape and you'll hear some ultrasound being produced if this thing is on. I don't know if you can hear that, but as I pull the tape, it generates ultrasound, which is kind of cool. It also turns out if you crack your knuckles, it will create ultrasound. You can learn a lot with this thing. So I have this board, and it is sending the ultrasonic communication. I'm going to hold this thing up. I might have to adjust the sensitivity a little bit on this board, but we'll see. That works pretty well. So it's actually two different frequencies and sound like Morse code to me. So that's actually sending a Morse code message through that LED of the, through that piezoelectric sounder without us knowing. And the reason I use two different frequencies is if I'm just going from off to on at some high frequency, you actually hear a click. If you walk up to like, they have those like gopher stakes that you put in your garden or things to scare away the skunks and whatever. If you go up to one of those things, you can actually hear the clicking because that's the ultrasound turning on and off. So I decided to just use two frequencies that are fairly close together. So when you put your ear up to the device, you don't hear that clicking as much. It's barely there. And that's the physical clicking of the element inside of the piezo element actually turning on and off. So if you can minimize that, then you get a more covert channel. So we'll go back to the slides here. If you want to build your own, you can use an Arduino. Again, the demo I had here was on a microchip PIC, but you can do it with an Arduino. The code is, at least to generate the ultrasound, is also very easy, just like the optical covert channel, where you're basically using a timer1 library, which uses the hardware-based modules on the Arduino to create much more precise timing. And you're setting your pin that's connected to your piezoelectric device, and then you are setting the period, which would then convert to the frequency of the square wave that you're generating. And then you can just send this command, timer1.pwm, and you're generating your ultrasound. So you roll that in with a Morse code generator or whatever other thing you want to try to get the data off of your Arduino, and you're done. Here's a link to the bat receiver kit. And yeah, super easy to build, and it has the schematics. You can go through and understand what it's doing. And it's using a divide by 16 binary counter to bring those high frequencies down. So everything's divided by 16. So that's a little bit of optical or of hardware-based covert channels that are out there. There are probably lots of other methods that we don't know about, which is why I have these question marks here. These are the ones that I know about and that are easier to explain. Hopefully, this gets you excited enough to go out and explore a little bit more, maybe create your own, and then maybe share that stuff with the world. So yeah, that is an overview of hardware-based covert channels. And thank you for being here. Thank you for watching. Either if you're watching now or watching later, thank you. Obrigado. And yeah, thanks again for having me.